Hi everyone, in this presentation I'm going to give a brief overview of our proposal for a quantum circuit to speed up the cryptanalysis of code-based cryptosystems. First of all, a little of background, why we choose to pursue this kind of research, because there are now quantum-resistant crypto schemes under scrutiny. NIST, for example, is pursuing a post-quantum standardization process, and crypto systems based on linear codes are among the major candidates to their apparent immunity to quantum attacks. For this reason, sound and precise evaluation of the computational effort required to break them using quantum computers is required. We implemented in our proposal a quantum circuit to accelerate the exhaustive search of Librical's algorithm. So what are these kind of code-based cryptosystems? They were originally taught as error-correcting codes, and a binary linear error-correcting code C is described to a parity check matrix H with sides R times N that is composed by all the n-length column vector C code words such that HC is equal to the 0 vector. A corrupted code word Y can be represented as an n-length column vector given by the sum of the original code word C plus a new vector, the error itself, E. And S, which is equal to H by E, is called the syndrome of the error. How can we derive trapdoors from these error-correcting codes? The syndrome decoding problem states that given H of a random linear code C and the syndrome S, we have to find the error E with weight of E bounded such that HE is equal S. In the pictorial representation on the slides, we can see that the weight of the error vector E is equal to T. The decision version of the SD problem, the SDP, was proven to be NPR'd by McAleese, and examples of PQ cryptosystems based on SDP are McAleese and Bike. The information set decoding up to now is the best structural attack against code-based cryptosystems. The first version was proposed by Pranger in 1962, and there have been around 15 optimizations since then. We focus our work on Librical's variant of ISD. So Librical's algorithm starts by guessing R columns of H, the so-called information set, corresponding to error bit position with weight T minus P. Then we bring the chosen column to the right of the parity check matrix H using a permutation matrix P and obtaining therefore a new parity check matrix H hat. Simultaneously, we apply the inverse of P to the error vector E, obtaining a new error vector E hat. After this process, we compute the reduced row echelon form of the new parity check matrix hat H. What we obtain is a new matrix H that is composed by a left submatrix with sides V with sides R times K, and a right identity submatrix with sides R times R. We encapsulate the performed row operations in a unitary matrix U, and we multiply the original syndrome S by U, obtaining the new syndrome bar S. With this new configuration, we have that V is multiplied by the top k bits of the error that we denoted by E prime, while the identity matrix E is multiplied by the bottom R bits of the new error vector, which we denoted by E second. So bar S is obtained through the XOR of V E prime and E second. We know by the assumption of Librical's algorithm that the weight of E prime is equal P and the weight of E second is equal T minus P. From this, by doing some math, we can derive that the weight of bar S XOR V E prime is equal T minus P. But E prime, we say that is a vector, a column vector with only P bits asserted. So this multiplication between V and E prime basically amounts just to XOR together P columns of the matrix V. So the idea of Lie-Bricker's algorithm is to do an exhaustive search through the columns of V, and basically for each choice of P columns of V, we XOR them together with bar S and check the weight of the result. If the result has weight T minus P, the algorithm succeeds. Otherwise, we start again with the new guess of a new information set. So what about the computational cost of this algorithm? It can be determined by observing that it is a randomized algorithm that always yields a correct output that is either the value of E or it informs about a failure in an expected finite runtime. The runtime of the algorithm is obtained from the probability that a run of the algorithm itself succeeds, that we denoted by PR sucks, and multiplying its inverse by the cost of a single iteration, which we denoted by C iter. The probability of success is determined dividing the number of permuted error vector configuration having P asserted bits in the first K position and T minus P asserted bits in the bottom R position, divided by the total number of admissible error vectors with length n and weight t. In parentheses, we found the computational cost of the information set guess. So it encapsulated the choice of the information set, the permutation matrix P, and reduced the row echelon form. The red part instead is corresponds to step 4, basically, and it's the cost of performing the exhaustive search of the algorithm K choose P times, because we want to do an exhaustive search through all the vectors with length K and weight P. So this exhaustive search, we can say that has an exponential complexity, and our goal is therefore to accelerate it through a quantum circuit, in particular using Grover's algorithm. But first, we need to rephrase the problem as a Boolean function as it is demanded by Grover's algorithm. Indeed, step 4 can be seen as a Boolean function taking as input an error vector x with length k and weight p, and it produces output 1 if the weight of the XOR of the columns of V indexed by the bit of x together with bar s is equal to t minus p or 0 otherwise. So in other words, the domain of our function is composed by all the possible choices of E prime. What about Grover's algorithm? Grover's algorithm tries to find the unique x star belonging to the domain such that f of x star is equal 1. X star is thought as a label of a basis states, id est ket x star. We start by creating a uniform superposition of all the domain basis states using a unitary transform P. Then we apply the so-called oracle stage, which is denoted by Sx star transform in our equation, that has the main goal of inverting the sign of the amplitude, so state x star. For example, here in the pictorial representation, we see that the only state flipped is this one. The diffusion step tries to increase the amplitude of ket x star, reducing simultaneously all the other amplitudes, and it can be rewritten as P S0 P minus 1, where S0 is the transform inverting the sign of the old zero state, and P is the previously seen input preparation transform. By repeating oracle and diffusion stage around square root of d times, we have a probability close to 1 of measuring the sought state, ket x star. Before introducing our quantum circuit, we recall in the top part the equation that we are the function that we are trying to implement. But first, in the first step is to prepare a uniform superposition of all the basis states belonging to the domain. In the original Grover's framework, we expect a uniform superposition of all the basis states with length k. So the size of the domain is exactly 2 to the k. But this implementation will produce many unwanted states, all the states for which the weight of the basis states is different from p. So we should have an additional check, in this case, an additional check on the weight of the input, and also an increasing number of iterations. For this reason, we want to create a uniform superposition of all and only the k choose p basis states for which the weight of x is equal p. This state has a name in the literature, and it's a Dickey state, and we implemented the proposal of Mukherjee of last year, which is an improvement over the previous best algorithm presented by Barshi 2 years ago. It requires px gates and big O of k plus p squared c naught gates and ry gates, with an overall depth equal to big O of k. The second step is to implement the oracle circuit, which is a black box in Grover's algorithm, but we need to implement it. And we need to implement a reversible circuit computing f, and at the same time flip the sign of the amplitude of the sought state ket of x star. We recall that at this point on the top k qubits, we have a Dickey state. So we want to use these k qubits to conditionally XOR the columns of the matrix V. And the idea is to use the k bits, each of the k bits as selector for a column of the matrix V. So each of the k qubits will select a specific column of V, which is transposed column-wise on the bottom R qubits. Then we add the result to bar S, and at this point we have to check the weight and set the result to 1 upon success. How do we check the Hamming weight of this set of qubits? We used a classical algorithm called fast population count that splits the input string x into substrings. Then we use another tree to compute the partial weights in parallel that iteratively add the partial weights. And at step P, the adders takes 2 input bit string and produce one single e plus 1 output bit string. We implemented for this reason the Cuccaro adder, which is a reversible variant of the Report-Curry adder proposed in 2004 by Cuccaro. A single adder requires 2 additional qubits, which is a carry out and a carry in, which is reusable by all other adders. A single adder also requires a linear number of gates. We also implemented an optimized 2-bit adder that requires 1 single C0, 1 CC0, and 2 X gates. In the top part of the slide, we see the quantum circuit corresponding to the Hamming weight check, Hamming weight computation for an input string of 4 qubits. We need R minus 1, which is equal to 3 additional carry out qubits and others. We need R divided by 2, which is 2 additional carry in that are used by all downstream others. The final sum is stored on log 2 of R plus 1, which is equal to 3 qubits. And we denote this set of qubits stored in the result as HV. At this point, we XOR into the HV register the ones complement of the binary representation T minus P. And in this way, if the qubits belonging to the HV register have weight T minus P, at the end of this stage, they will be all in state ket1. And it will be useful to use them as a controller, as we will see in the next slide. Indeed, at this point, the idea is to use the qubits belonging to HV in a multi-controlled set, using one of them as target and all the others as controls. And in this way, we can invert the amplitude phase of the sought state ket of X star. In the tables here, we can see the equation corresponding to the different gates for the different subcircuits. We note that the depth does not depend on P, while the number of gates depend on P squared. The MCZ gates is not shown, but we have just two of them, one in the oracle phase and one in the diffusion phase. The number of qubits is equal to k plus 2r, plus an additional k when we want to translate the MCZ into physical gates. To validate our circuit, we use the Atos MyQLM, which is the open source version of the QLM linear algebra simulator, capable of simulating up to 32 qubits. We test the Schoolbook 743 Hamming code that is capable to correct up to t equal 1, but also we properly crafted linear codes able to correct up to t equal 2 error bits. And both the quantum circuits alone and the whole Liebigker's algorithm were tested. Also, we consider the parameter set for each of the NIST security levels for both classical McEliece and Bike. For both of them, we exhaustively searched for the optimal value of P, minimizing the number of gates, which is different from the classical P equal 2. The NIST security level are defined in this way from NIST call. Any attack that breaks the relevant security definition must require computational resources comparable to or greater than those required for key search on a block cipher with 128-bit key for level 1, 192-bit key for level 3, and 256-bit key for level 5. So in the table summarize our result for the quantum circuit only. We can see that at most 2 to the 17 qubits were used, which is feasible or expected to be feasible even for near-term quantum processors. The depth of Grover's circuit for Bike, we stress that is below 2 to the 40 required by NIST, which is thought to be the most strict limit for implementing a quantum circuit. When considering the whole circuit, we expect to execute n choose t divided by k choose p, r choose t minus p, different quantum circuit, because we have in input different v n bar s. Ideally, having the same number of QPUs, we can run all iterations in parallel. In practice, we can see that there is a high degree of parallelization. And this table instead shows the cost of the overall computation, considering a probability close to 1 to observe the correct state. So it's takes into account also the classical part. And we compared our cost against the estimated gate count for the classical only algorithm, and we can say that there is gain in our algorithm, but not so much. And we also compared our costs against Bernstein full Grover proposal that has only asymptotic values. So to conclude, this is, as far as we know, the first design of a detailed quantum circuit to speed up ISD. And we use the classical quantum mixed algorithm implementing Liebigker's variant of ISD. We should stress that the number of gates on the real QPU might slightly change depending on which physical gates are actually available. It is interesting to investigate in future if a quantum circuit for the remaining part of Liebigker algorithm, so the classical part, is viable and convenient with respect to the classical counterpart.